Hey friends, welcome back to the week 4 of chemistry. It's good to have you guys back and joining me for this series of lectures and lessons. We've come a long way since we began this unit of chemistry, and I know there's been a lot of information thrown at you. You guys are doing great, and I think you've probably absorbed a ton of information. And I think I just want to encourage you to keep going. And it's a lot to take on the first time around with chemistry. But the more you do this, the more you will absorb. There'll be layers of information that's added each time you do anything related to chemistry. So if you're finding it just to be a lot, just continue on the best you can. I believe in you all. You're doing a great job. So right now, in this first video for week 4, we're going to focus on learning about acids, bases, and pH. So by the 1600s, chemists had figured out that compounds called acids and bases are very different. In 1909, Danish chemist Søren Sørensen introduced the pH scale as a way of expressing acidity and alkalinity, or the concentration of hydrogen ions. pH is sometimes referred to as the potential of hydrogen. Acids are known to have a certain set of properties. So if you look at this slide, some of the properties of acids is that they produce a positive ion in water, an H+ ion in water, and they taste sour. They react with metals to produce hydrogen gas. They form electrolytes in water. They react with bases to form a salt and water. They have a pH that is less than 7, and they turn blue litmus paper to red. So the physical properties of an acid is that they would taste sour in an aqueous solution with water. They have a pH of less than 7, which is neutral. Let's go back and have a look at that pH scale again. So if you look at the pH scale, right in the middle of the pH scale is the number 7, which would be pure water. So acids will fall below 7 in the pH scale. And they will turn litmus paper red, and they conduct electricity when dissolved in water. The chemical properties of acid are that they will react with another compound called a base in a neutralization reaction to form a salt and to form water. So we can see this. Oh, there's another list of some common acids and bases. We'll just take a look at this for a second. So in our home, you'll have most of these things. So you have pure water in the middle again, and on the acid side, you'll actually have bananas, milk, tomatoes, grapes, lemons, and towards the higher end of acids, a stronger acid would be our stomach acid. And then on the base side, we have eggs and baking soda and things like our soaps and cleaning detergents. So again, talking about the chemical properties of an acid will react with the base in a neutralization reaction to form a salt and water. Bases will also react with metals, corroding them and eating away at them to form a salt and hydrogen gas. So you can see in this example, we have hydrochloric acid reacting with magnesium. to form magnesium chloride, a type of salt, and hydrogen or hydrogen gas. Acids will also react with compounds called carbonates to form a salt, water, and carbon dioxide. So here we have hydrochloric acid, we have a carbonate called sodium carbonate, and that will react to form sodium chloride and water and carbon dioxide. So there were 3 products from this reaction. Nobel Prize winner Svante Arrhenius, a Swedish chemist, developed the early definition or understanding of what exactly an acid or base is. So here we have a picture of Svante Arrhenius. By Arrhenius's definition, an acid is a substance like hydrochloric acid, or HCl, that dissolves in water to produce H positive ions. A base, alternatively, dissolves in water to produce or donate the OH negative ion, or a hydroxide ion. So here we have an example of an acid that is dissolved in water. And this acid, HCl, is going to dissociate in solution with water into its ions. So it's not super clear on this slide, sorry about that, but you have the acid in water will break apart into its ions, or its electrolytes. So an acid is sour in water because it dissolves in the water and dissociates into its ions or electrolytes. This is what makes it a good conductor of electricity, actually, because it dissociates into its ions. We know that acids can range in strength from weak, like vinegar or acetic acid, and urine, to all the way up to hydrochloric and sulfuric acids, which are very, very strong acids. When an acid is dissolved in water, the hydrogen atom that is part of the acid exists in the water as its H+ ion. But actually, the hydrogen atom attaches to the water molecule to form what's called the hydronium molecule. Oops, here we have some common acids, strong and weak acids. So some of the weak acids would be formic acid, acetic acid, sulfuric acid, or phosphoric acid. But the strong ones like hydrochloric acid and sulfuric acid and chloric acid. So there's a whole range of different kinds of acids. Here we have the water molecule, and when an acid is added to the water, it will dissociate and it will give up its proton, which is its H+ ion, and it will form the hydronium molecule. So it will actually exist as H3O in the water. So once again, hydrochloric acid dissociates in water to form its ions H+ and Cl-. This is a very strong acid and will not only react with and corrode metals, but it will also react with skin. So acids are something that we have to be very, very careful with when we work with them. There are some that are completely safe to work with, like vinegar or lemon juice is actually a pretty strong acid, but it's okay in small amounts. Hydrochloric acid is found in our stomachs, actually. It is used to digest our food as part of our digestive system, but it's also very important as part of our body's defense system, killing any pathogens or infectious agents that enter through our mouths. So the hydrochloric acid is actually acting to digest foods, but also as one of the barriers used in our immune system. So bases are different from acids, and they are almost the opposite of acids in many ways. Here are some properties of bases. They produce the OH negative ions in water. They taste bitter or chalky. They also dissolve into their electrolytes in water. They'll feel soapy or slippery on your skin. They react with acids to form salts in water. They have a pH greater than 7, and they will turn litmus paper blue, or it's called basic blue. So once again, the physical properties are that they taste bitter when dissolved in water. You should never ever taste a base. You should never test this out, okay? Bases are very, very dangerous and can cause severe skin irritation and damage to your skin. If you get them on your skin will feel slippery. And that's because it's called caustic. Bases are caustic. And they're actually, one of the chemical properties is that they dissolve fats and lipids. And so that's why they feel slippery on your fingers, because they're actually reacting to your skin. Bases will change litmus paper to blue. They have a pH that is higher than 7, and they, just like acids, so this is one of the similarities, is that they can conduct electricity when dissolved in water. Their chemical properties, once again, is that they will dissociate into their ions or electrolytes when dissolved in water. Okay, so here we have on this slide, we have NaOH. This is a base that's dissolved in water. So it's sodium hydroxide. And when it's dissolved in water, it will dissociate into its ions. So you'll have the hydroxide ions and the sodium ions, or electrolytes, as we know them in water. Again, one of the chemical properties of a base is that they dissolve fatty substances like grease, which is why a base is often in our cleaning products. Bases act the opposite way that acids do, in many ways. Like acids, though, you can have a weak base and a strong base. And an example of a weak base is sodium bicarbonate, which we know as baking soda. We use it a lot in baking. And a strong base would be potassium hydroxide, or KOH, which is chlorine bleach. Did you know that when seafood begins to break down, weak bases are being formed, and that is what gives seafood its fishy odor when it starts to break down? So once again, bases will react with acids to form salt and water. And here we have another example of an equation of an acid, HCl, that's hydrochloric acid, and NHO4, which is, I can't remember what the name of it is, ammonium hydroxide. So hydrogen chloride will react with ammonium hydroxide to form ammonium chloride and water. So the strength of an acid or base is determined by what percentage of the compound will dissociate into the ions. And here's another example of what's called a neutralization reaction. We have the acid and the base, and they're both in solution with water, which is why we have the A and the Q here in brackets, because it's an aqueous solution. and they react to form a salt and water. So when acids and bases react together, that's a neutralization reaction. They are acting on each other to neutralize each other. And they will form water and another ionic compound, which is called a salt. So here we go. We have strengths of acids and bases. Strong acids completely ionize, will 100% ionize in aqueous solution. So something like hydrogen chloride, when it's put in water, it will completely come apart in the water. A strong base will also completely dissociate in water into its ions or electrolytes. So the reason that we can handle weak bases or weak acids is that when they're put in water, they don't completely break apart because they're so unstable. They'll go back and forth. A compound of a weak acid will come apart, but then it'll come back together. So you only have a small percentage that is ionized in the water at any given time. So I hope that makes sense. In 1923, another definition was developed for acids and bases. Simultaneously, but independent of each other, Danish chemist Johannes Bronsted and English chemist Thomas Lowry proposed that acids are any compound that can donate a proton, and a base is any substance that can accept a proton. So according to this new definition, an acid can only behave as an acid in the presence of a base, and vice versa. This definition included a lot more compounds that had up to this point been left out of an acid-base definition. It also meant that an acid did not have to donate a hydrogen proton. It could donate a different kind of proton. And that a base did not have to have a hydroxide ion as part of its compound. So basically, in the Bronsted-Lowry definition, a base is a proton donor, and this is wrong actually, that the base is a proton acceptor and an acid is a proton donor. So this slide is actually wrong. Sorry about that. Okay, that almost brings us to the end of this week's first video about acids and bases and pH. But I just want to show you a couple demonstrations. In your assignments this week, one of them is to do it's called the Browning apple experiment. And unfortunately, you can't see it very well. I haven't let this apple sit out for very long. But I treated one side of this apple with lemon juice, and I left the other apple without anything on it. And so I know that you probably won't be able to see this at home, but on one side we have what's already happening. You've probably all seen it, right? When an apple is left out to the air, it turns brown, and this is called an oxidization reaction. But if you add lemon juice to it, it slows that reaction right down. And so in your apple browning experiment, you guys are gonna you're gonna try this on your own, and you're gonna let an apple sit out and test, and just see for yourself what happens when you add an acid like lemon juice to an apple. Okay, and now we're going to do another demonstration. This is another hands-on activity that you guys are going to try, or you can try at least, at home this week yourself. I am going to turn this around. Okay, I don't know if you can see it at home, but we have 6 test tubes here. and I've labeled them 1 through 6. Number 1 is filtered water. Number 2 is acetic acid or vinegar. Number 3 is citric acid or lemon juice. Number 4 is milk. Number 5 is a sodium bicarbonate solution, so it's in water. And number 6 is laundry detergent, also diluted with some water. Okay, so what I did, and what you're gonna do this week, one of the experiments that you can try is I made an indicator. An indicator, we talked about litmus red or litmus paper. Litmus paper is one type of an indicator which will show if something is acidic or a base. And we made our own indicator here at home using purple cabbage. So I just boiled some purple cabbage and made a solution of that. And we're gonna use this as our indicator. So I'm gonna put a few drops of indicator in each of these test tubes. So the first one is our filtered water. And make sure I put enough in there so that you guys can see this at home. So this one is the lemon juice right now. Now is number 4, this is our milk. And then we have sodium bicarbonate. And the last one is our laundry detergent. Okay, I'm gonna give them a little stir. Oops. And last one is our laundry detergent. Okay, so now we can have a look at them and compare them to, this is the pH scale that it would go along with using the purple cabbage as your indicator. Okay, so it may not look exactly like the pH scale that I showed you earlier, the slide. It has its own colors. So what I would have hypothesized is that we would definitely see different colors ranging depending on the acidity or alkalinity of the compounds that we've used. And of course, comparing it to our water. This is my filtered water, and this one, as you can, if we compare it to the screen, is slightly purple. So it would definitely fall right around the pH 6-7, right around that pure or neutral pH. The next one we did was the acetic acid. And definitely if you can compare this to the pH scale, the indicator there, it's kind of that pink color, and it would definitely fall around the 2-3 pH. Then we had the lemon juice, and lemon juice should definitely be more acidic, we would assume that, and it definitely would fall more towards the 1 to 2 range in the pH scale. Milk, I would expect that milk would fall right around the neutral as well, and I would say that it does, slightly basic. Sodium bicarbonate, we know that that one should also be more alkaline. And as you can see, the sodium bicarbonate definitely would fall right around, I would say around the 9-10 on the pH scale. And here we have my laundry detergent that I made in solution with water. And I would have expected that this one would be more base and would be more alkaline. So probably I thought would be definitely in the green to yellow sort of range of this scale. I'm a little surprised that it falls more in the neutral range. So that's, yeah, a little bit surprising. So you're gonna try this experiment at home. It's actually really fun because you get to make your own indicator and then you get to test out your own compounds. And I would say, you know, try whatever different things you have in your home. I mean, there's so many different solutions you can make. There's so many different beverages you can test out. And just have fun with this. I mean, it doesn't take a lot of purple cabbage to make a lot of indicator. So you could try all different kinds. And please record your findings. And if you want to send me pictures, that would be great. I would love it. Okay, have fun with this, and we'll see you soon.